Hi, welcome back everybody. This example 11.9 is actually a continuation of a previous problem that we most likely did in class, or maybe there was a previous video for it, but this is a continuation of one. Actually, I'll show you the original one right here. All right, so this was also called 11.9, but it's just a continuation of it. So in the first part of the problem, we solved for what the angle had to be. Now here it's called phi. I think we wound up calling it theta. In fact, I'm going to change that to say theta right now. So let's go ahead and draw over that. There we go. And we'll call it theta. And it was the angle at, or the angle theta at which the ladder is the most stable. All right, I shouldn't say the most stable, but it's the least angle at which the ladder is still stable. So we solved for that angle, and we came out with the fact that theta was going to be equal to the inverse tangent of 1 over 2 times the coefficient of static friction. Because really, static friction, I'm going to use a little different kind of cursor right here. There we go. The static friction that acts right there from the other side is really what's keeping it from sliding down. All right? If there's no friction on the floor, then this thing just slides right down because, of course, it says the wall is frictionless right there. So let's use this assumption right here to attack the part of the problem that we're going to be working on today. Okay? All right, let's move forward. So the hard part of 11.9. What's happening here? And again, we still have the assumption that theta equals the inverse tangent of 1 over 2 mu s, coefficient of static friction. A person is walking up this ladder. This ladder is at the minimum angle, all right, and a person is trying to walk up some distance right there. Okay, they're going to be walking up distance d. And so the question is, how far up is d? How far up can they walk such that the ladder actually still remains where it is? If they step near the bottom right here, they're actually increasing the normal force of the floor and therefore increasing more friction. But as they move up towards the top, there's kind of like a rotational element of it that will cause this top part to want to slide down. So at some point, d right here, that furthest distance is the distance at which somebody can walk up and actually have it still be stable. Okay? That's what we want to solve for. A couple things I want to kind of write in here. This length from here to here, we call that L. That's the length of the ladder, right? Let me draw that sideways. Length L, okay? This distance D right here is the distance we're solving for. This angle here should be theta. It's marked as phi right now. I'll just go ahead and get rid of that. Right, that angle should be theta. And the mass of the ladder is capital M, but now we have a person. So let's see, big M equals the ladder. Small m, lowercase m, is going to be the person. All right, the mass of that person who is walking up the ladder, that distance d that we're solving for. Okay? All right, I think we have all of our dimensions marked on here. Let's mark some of the forces that are acting on this. And I'm going to use red to mark the forces so they kind of stand out. What's one force that's acting on the ladder? Well, the ladder itself, right? The ladder is mass, this capital M right here. Now, where do we assume, or where do we act like the mass is acting? Now, clearly, there is mass all along the length of the ladder, but for our purposes, we can pretend like the mass is acting at a single point right in the center of the ladder, and it's acting straight down. We're going to call that big M, G, okay? So the ladder itself is trying to pull itself down, just trying to fall. That's what we used when we did the first part of this problem. But there's also a mass of the person. Right? Now the person has moved up to distance D right here, to point D. So that person's mass, it's not very good arrow, let's try that again. The person's mass is acting downwards as well. And that's a lowercase m, G, that is acting right there. So you get the mass of the ladder acting down, the mass of the person acting downwards. We also have the normal force from the wall. All right, I'm going to draw it kind of coming out of the wall like that. All right, and I'll close that arrowhead right there. Call that N W, normal force from the wall, because the wall has to sort of provide some force back. If the wall couldn't do that, the ladder would just kind of flop right down. So the normal force is providing a horizontal, so the wall, I should say, is providing a horizontal normal force. Okay, any other forces? Well, there's got to be a force supporting this, right? So it's normal force from the floor. So NF, I'll call that's an F right there. I don't know how that kind of got kind of goofy. Normal force from the floor. It's still kind of weird looking, but you get it. And what else? We also have the friction force supplied from the floor. F sub S. That should be a lowercase f. Static friction force, which is keeping the ladder from sliding in the first place. Okay? All those forces are acting on this ladder to keep it in stasis, to keep it from rotating or from sliding down, translationally. Okay? So we're going to use net torque to figure out what this distance is right here. All right? We've got a force acting at a distance. We should be able to solve for that distance right there. We've got a bunch of various other forces acting at distances as well. So where would be a good place to put the axis of rotation for this torque? Now, if you recall our rule of thumb, first of all, you can put the axis of rotation anywhere you want along this right here. All right? And sum your torques around it, and it should come out to be the same. But our rule of thumb for picking a good axis of rotation is pick a place where you have the most forces acting, or the most complex forces acting. That would be right here, right down at the bottom. Now I'm going to draw the axis of rotation in orange right there and mark that AOR. Okay? And the reason we do that, the most complex forces, is it makes those forces, it drops them out of the torque equation because they're not acting at any radius from the axis. They're acting right on the axis. And so they're not creating any torque. So it's just this force, and this force that are acting to create the torque around this axis of rotation that we decided to be right there. All right? And hopefully that should help us to find this distance d. So if this is our axis of rotation right here, and this is our kind of radius, the ladder is our radius, we have this distance d, the length L, well, another length in a minute. Are these forces acting at right angles to the ladder, to the radius? No, they're not. They're at these little acute angles there, right there, and this is kind of an odd angle from the ladder. We want to turn these into right angle forces because we have to account for the fact that the radius and the force are not at right angles. So we need to bring in some trig functions to account for that angle. All right. So let's start. Let's start right here at little mg. All right. What would the perpendicular, lose my train of thought, component of that be? Now I drew a little open arrow right there. That's supposed to represent a component of little mg. What would that be? We're drawing it that way because we want to make that at right angles to the radius. But what would that be? Well, that would be mg, and I'll write it in sideways here. Mg cosine of the angle theta, right? We recall that from friction and inclined planes, right? That we would call that our perpendicular force. Well, the same thing would be true with big mg right here. Big mg cosine of theta is acting right there. And again, we drew it that way because that is presumably at right angles to the radius. And then we can just kind of multiply them together to the force times the radius. Finally, we have this guy up here. There's a normal force being supplied from the wall. The wall is trying to make the ladder, the wall is pushing back on the ladder such that it's trying to make it rotate clockwise around this axis of rotation. But we need to turn this into a perpendicular component of that force. So I'm going to call it that. Normal force from the wall. Okay, what trig function is this going to be? It's clearly perpendicular. And down here we did the perpendicular forces by using cosine, but remember these were based off of vertical forces. Normal force from the wall is a horizontal force, and so the perpendicular component of that would be NW sine, I almost said cosine, sine of theta. Okay? This problem required a bunch of setup, and we just did it. All right, the rest of it is actually quite, I won't say easy, but it's It's really just algebra from here on out. Once we sum our torques around this axis of rotation right there. All right? Okay, I'm going to shrink this down now. Give myself a little bit more space. That being said, let's now make a statement about, hopefully you can still see that. You probably have it written in front of you. Let's make a statement about the net torque. I'm going to do this in, what color is that? I'll do it in red. Okay? So the net torque around that axis of rotation, we're going to presume to be 0 because we don't want that ladder to be sliding. All right? Net torque is equal to, I hope I don't run out of space here. I think I just might. Let me erase this stuff for a second. I'm going to shrink this down yet even further because this setup is going to require a lot of space. All right, the net torque equals 0. The net torque is also equal to, all right, now we have the forces, various forces times their distances, okay? Let's just work up from the axis of rotation to the furthest point, all right? What's the first force? It's creating a right angle force to the radius. That's our lowercase or small mg cosine theta, right? Little mg cosine of theta. I can see this is still going to, I'm going to back up here again. I'm going to delete something else. I'm just going to start at the bottom because I'm going to need a lot of space to write horizontally. I'm going to start right here. Sorry about that. Net torque equals 0. Net torque equals, all right, that first force, right angle mg cosine theta, that guy. Mg cosine theta, acting at what distance? It's acting at distance d, which, by the way, we're solving for, right? Distance d. Plus what else? Well, moving up, we have this perpendicular component of the ladder's mass, mg. So that's going to be big mg cosine theta. Mg cosine theta. Acting at what distance? What distance is that from the end? We don't really have it marked right here, but we know, right? That distance is going to be half of the length. So that distance is L divided by 2. And those pen strokes don't quite match, but that's all right. So the distance that the mass of the ladder is acting is L divided by 2. So let's just go ahead and write that in. Times L over 2. Minus, so these are creating positive torques, right? Counterclockwise, counterclockwise. This guy right here, the normal force from the wall times the sine of theta, is creating a clockwise torque around the axis of rotation. So that's going to be NW sine of theta. At what distance is that acting? That's distance L, right? Distance L times L equals 0. Okay? I had an inkling that I was going to need more space, so that's why I kind of restarted at the bottom right there. Okay. So we have taken force times distance, and force times distance, and force times distance, and we're trying to solve for that distance d right there. Okay? I'm going to add this to the other side, NW sine theta. And you know what? I might just find use for this space up here at the top anyway a little bit later. All right? So we're going to say that mg cosine of theta times d, times our distance, plus big mg cosine of theta times L over 2 equals the normal force from the wall sine of theta times L, times distance L. Okay? Now, we have these cosines and sines right here. All right? These both have cosines next to them. Sine is right here. Well, they're different kind of terms, different expressions, but what expression involves cosine and sine? That's tangent, right? Tangent is sine, oops, I forgot my theta in there, sine of theta. Tangent is sine over cosine, right? So if I divide that by cosine of theta, and that by cosine of theta, and that by cosine of theta right there, these guys will go away, and this right here will turn into a tangent. All right? So we're going to have mg times d plus big MG times L over 2 equals the normal force from the wall times, I'm going to put the L first. I'm going to bring the L over next to the NW, times L times the tangent of theta. Okay? All right. We have some things in here now we can actually substitute in. All right? First of all, let's look at theta here. All right? What is our theta from the first part of this problem? Theta. Well, theta is inverse tangent of 1 over 2 mu s, or 1 over 2 times the coefficient of static friction. So, if this is the tangent of theta, and theta is the inverse tangent of all this right here, the tangent of the inverse tangent makes them basically go away and cancel out. So, this whole expression right here is basically going to be 1 over 2 mu s, 1 over 2 times the coefficient of static friction. Okay, so let's write it like that. In fact, I'm going to kill two birds with one stone here. I'm going to say that this, I'm just going to write that in, that's 1 over 2 times coefficient of static friction. All right, we established that from the first part of the problem. But the other bird that we're going to kill with a stone is this normal force from the wall. This is kind of an oddball expression right here. We don't have anything else in terms of n, right? How's that going to cancel out or go away or be made easier? Well, we can describe what n from the wall has to be. Look at our diagram up here. The normal force from the wall, this is the actual force that the wall is applying directly outwards in the x direction. What does the normal force from the wall have to be equal to? It's got to be equal to the static friction force. This is the only thing, the only other force that is acting horizontally to keep the whole ladder from sliding down. So the normal force from the wall equals the static friction force. Okay? Normal force from the wall. Well, how do we find the static friction force? The static friction force is the mu, right, our coefficient of static friction, times mg, right? So it's mu s times mg. Well, what is the mass that is acting downwards right here to create that static friction force? The masses that goes in there are the combined mass of the ladder itself, but also the person. So when we actually make our statement for the normal force from the wall, that's going to be mu s times, by the way, this is kind of our generic description of static friction force, right? We've got our mu s right there, and so our mass is going to be little m plus big M. They're combining to create even more static friction force on the floor, and then times g. Okay? You still with me on this? All right, so why are we bothering to say this right here? Well, because we can take this now and substitute this in for our normal force from the wall. Okay, so it's going to look like, so I'm going to do two substitutions right here. I'm going to stick this in, let's see, put that right in there. And the other substitution that we already talked about was we're going to put this in for the tangent of theta, right? Because the tangent of the inverse tangent of something equals to something. Well, that something is 1 over 2 mu s. So let's write all this out with our two substitutions put in there, okay? So that means it's going to be mg times the distance d, which is what we're solving for, plus big mg times L over 2 equals, here's where we substitute all this in for the normal force, the wall, mu, not a very good mu, let's try that again, mu s little m plus big M times g times that length L, that's right there, and then our tangent of theta becomes simply 1 over 2 mu s. 1, 2 times our coefficient of static friction. Okay. Well, what can we do now? Well, this is pretty simple over on this side. Let's see if we can make some sense of this right here by combining some things. We have this little m and this big M locked up in this parentheses right here, multiplied by mu s times g times L, and divided by 2 mu s. Oh, by the way, what can we do with the g's right there? There's a g there, and a g there, and a g there. That makes it simpler, okay? So on this side, we're going to have lowercase m times mu s times L divided by 2 mu s, and the same thing with big M as well, okay? So let me rewrite this. So m times d plus big M times L over 2 equals, all right, I'm going to distribute the lowercase m to all this other stuff. So m times mu s times L divided by 2 mu s. And now I'm going to distribute this big M. Big M times mu s times L all over 2 mu s. All right? Hey, we can cancel some things out now here, right? That's going to go away. That's going to go away. So we have now ml over 2 right here. Why does that sound familiar? Well, because we have it on this side too, ml over 2. Let's just cancel all this and all that. I'll put 2 slashes through it because we double canceled right here. We canceled the mu s, but also the rest of that fraction right there. And then we wound up with md equals ml over 2. Well, I think there's one more cancellation we can make. If md equals ml over 2, our m's go away. And our distance, the distance that a person can walk up this ladder at its minimum stable angle, is L over 2. All right, they can walk up right up to that center of mass right there. And now, I wouldn't try this at home, all right? But according to physics, that's the distance you should be able to walk up. Up to this point, you're actually creating more static friction, okay? But beyond this point, you're creating a torque that decreases the static friction and actually makes the whole thing kind of want to slide counterclockwise, and it'll fall down to the floor. So that's our distance d, simply L over 2. It doesn't matter what the masses are. Also doesn't matter what the length of the ladder is. The distance is L over 2. It can basically walk up, a person can walk up to the center of the ladder's mass and be perfectly fine. Presumably. But again, don't try this at home. Hey, thanks for following along. This has been a long one, but it's a good application of summing net torque and also some good algebra and trig skills as well. So, again, thanks for following along. Ask me if you have any questions, and I'll see you on the next one.